Hey, welcome back to Introduction to Computer Networks. This is Polly again. So this is week 6. Let's check out the announcements as usual. And although this is Wednesday, but we do have a couple things we'd like to communicate. First is the intro C and earnings. Okay, so this you guys know where it is already. We ask you particularly to go to the participation sheet of the Google spreadsheet and check whether the team numbers and the student IDs of the members are correct. Okay, so that's equivalent of going here. So let's check out the intro CS earnings Google spreadsheet. So down below you will see that there are 4 worksheets. Go here, the participation worksheet. So finally we have the teams and the members of the team list ready. Okay, we are not sure if there are errors because the first couple weeks are again chaotic. So please double check and let us know. Okay, and hope that everything is all right. Now, number 4. Next week. Okay, today we'll start talking about the application layer protocols. So next we will continue and begin to talk a little bit deeper about the application layer protocols. There will be a couple protocols that require that you guys know about the public key cryptography. So some of you might not have the background yet. So Polly has prepared a short playlist. So this is 3-4 short videos. You can probably skip the last video so that you get a rough idea how the public key crypto works. Okay, good. And today we're gonna start from quiz number 6. Okay, so let's go to the whiteboard mode. All right, so this is quiz 6. What you're seeing here is the output of traceroute. Okay. This is the same thing from the video we played yesterday, and I think it's the same example from the textbook. Okay, so what Polly asked you to do is just to exercise and recall a little bit, okay, of traceroute and how it works. Q1 here asks, we see that there are 3 measurements coming out of probing each hop along the way until the destination using traceroute, right? Why? How come the 3 measurements are not quite the same, right? They are the same hop. Suppose the delay should be the same, but they all come out somewhat different. 1, 1, 2, for example. 22, 18, 22. How come they are not always the same? Q2. Observe the delay measurements to hop 10 and delay measurements to hop 11. I think that would be these and these. So some of the measurements, no here. So this is 121 millisecond to hop 10. But this one is obviously longer than any of the measurement we see go in longer to hop 11, right? Hey, the intuition says that going to a closer hop should take shorter time. A farther hop should take a longer time. So how come sometimes, okay, the delay to a nearer router can be longer than the delay going to the farther away router? Now, last one is a little bit open-ended. I ask you to estimate the delay between hop 3 and 4. So hop 3 to hop 4. Just the delay from hop 3 to hop 4. And know that I'm asking for one-way delay. Know that these delays that the traceroute show are all round trip, right? The time it takes to send all the way until receiving a reply back. And I ask you also, maybe applying the method you designed to estimate the delay between hop 3 and 4 to do the same for hop 8 and 9 and see if it works. If it doesn't quite work, maybe you want to revise the method you come up with. Okay, so Q3 is asking the estimated delay one way between hop 3 and 4, hop 8 and 9. In the meantime, also telling us the design of your method. Okay, got it. And this one is going to be, especially for Q3, it might take a bit time. So that's allocate 5 minutes. All right. So 5 minutes, we are 10:25, and that's start counting time. All right, let's see. Okay. By the way, Ellen here says that for Windows, traceroute is actually called traceRT. Okay, so if you start the command line and type traceRT, then you can also do a traceroute to a particular destination. Okay, let's see. Team 10 says for Q1, because they are 3 independent packets. Yeah, that actually happens at different time, right? So at a particular time, the round trip delay is this, and another time, right? There could be some cross traffic here there. The delay might not be identical. And actually, the chance is higher that the delays are not hierarchical. Okay, and these variation mainly can come from queuing delay, as you heard from yesterday's videos. It really depends on how much traffic there are. Q2, the packets are not sent simultaneously exactly. So the packet may be busy suddenly, or the network can be busy suddenly. Yeah, it really depends on the dynamics of the background traffic, right? Yeah, so therefore they can differ. The router, there's another reason for Q2. The router may become busy and the priority of the traceback message is quite low. Oh, interesting. Yeah, it really depends on the setting of the routers, okay, of the particular router that you travel. Yes, I know that there are some routers setting these control messages to lower priority. Definitely. Yeah. So this could be due to the configuration of the routers. So it can be because of the background traffic. It could be because the packets are sent at different time of the day, that the routers are busy in different way. And if one is more busy, the responses can be delayed. Okay. The estimation. So I think Team 10 is doing a pairwise subtraction and then taking an average of the pairwise subtraction. And because this is one-way delay I'm asking for, so you divide it further by 2. Good. The same method is applied to calculate the delay between hop 8 and 9. And the outcome is actually negative. So you've explained. You can find that A9 is negative, delay to between A and 9 is negative. And this is physically impossible. So this is actually a kind of estimation. The real delay is not an exact number. It has variance. Indeed. Okay. So now you know in a system, right, that is very dynamic like this, to measure delay, one-time measurement is definitely not saying much. So even though that given this measurement, you can calculate something, but what you can see is very much that this is probably not going to be sufficient, okay? Or the estimate coming out of it is probably not reliable, reflecting the real delay, right? So let's see, Team 13. Yeah, one may encounter different traffic loads from one probe to another probe. Therefore, the delay come out differently. Because the queuing there, the returning packet experience or the going packet experience might be different. For Q2, the reason the same, right? So in case when the second probe to router 10, second probe to router 10 experience a lot more queuing delay, right? Then the 3 probes to route 11, then you get longer delay. Yeah, okay, so the method is a little bit different. So this time, Team 13 is saying that that's add all 3 delays together and subtract the 2 groups of delays and then divide it by 3 divided by 2. Okay, so the calculation is a little bit different. So it's almost like taking average delay to hop 4, average delay to hop 3, and then subtract them. But once again, if we apply the same method to the pair of 8 and 9, then we get negative estimates. Yeah. Let's see, team 2. 3-probe package sending, you have significant different delay. Yeah, so I guess the point is very straightforward and simple, that these 3 probes are just different. Okay. 11 might be less busy than 10. Yeah, so the second probe to router, the probes to router 11, the delay might be shorter than the probes at the time they are sent to router 10. Yeah, similarly, right? The time that the router 11 received the messages, the router is less loaded, return faster. But router 10, upon receiving the second probe, it could be a bit busier. So you see that there's probably queuing delay somewhere along the path, or router-specific delay. Here we see similar estimations, I guess. Yeah, taking the average, and get about 4 milliseconds here. Similarly, so I guess team 2's solution is almost the same as I will actually isomorphic of team 13. Okay, guys, what would you suggest that we measure in a reliable way? Q1, traceroute will throw 3 distinct packets. They happen at a different time, therefore the delay can, of course, be different. And the router's business can be different too, of course. Yeah, so the setting, so especially for busy routers, very often they set higher priority to CS traffics and lower priority to the control traffics. Especially the kind of packets the traceroute send, that's actually called the ICMP packets. And that's just, for those are the traffic just to check things, how things are. So they are definitely set to lower priority most of the time. So I guess that you now see that you can use the same explanation for Q1, for Q2 as well. Oh, okay. So actually the second reason from Ting-Qi, team 5 is different. So Ting-Qi is saying that the route going one way versus the way coming back might not be the same. You know what? That is very much the case on the internet, especially when you send traffic out of the country. This is very likely true. Okay, the way the outgoing and the incoming direction, the path can be different. Yeah, and you know what? This is hop 8 and hop 9. So this is this is hop 10 and 11, far away destinations. So chances very high that these are different. Yeah, so maybe the way going slightly different, the way coming back slightly different. So this is also suggesting that routes can be different. Now, in case when you're sending a particular probe, the route is different, of course, the delay very likely different. And from the demo Polly showed in the video yesterday, right? Polly was actually just trace routing to google.com, which is not far away. And I see in one of the hubs, there are actually 3 different routers doing the forwarding, right? Within a short period of time, just within a trace route. See, the route differences can be because of how the routing protocols work. It can also be because in that demo's example, chance is very high that the ISP, okay, that my traceroute packets are going through, they for some reason do some load balancing so that they forward packets in this way, and so to balance the that particular hub, okay, and the load is distributed to 3 different routers. And there's also a chance that after the 3 different routers, the next hub can further be different. But in our case, in the demo's case, they are the same. So they are just 3 routers sharing the load. So that's one way to reduce the cost, okay, maintaining an ISP's backbone. All right, so very interesting. Guys, we don't have that much time to go over all of you guys' solutions. If you guys are curious, check each other's solutions out. You might find some interesting solutions later. Yeah. Team 23, wow, very elaborated. Yeah, but I guess that people find that it's a little bit odd if you use simple method, okay, and applied it for a pair of hubs, and it works, but for another pair of hubs, it doesn't quite work, right? Yeah, so all of you come up with something that's negative. So I guess you use the same method, okay? The values can be a little bit different though. Yeah, there's a slight differences. Oh, interesting. Okay, to 1018, I guess what you're trying to say that there's so router 8 and 9 can potentially be very close. If they are far away enough, then the chance of having a negative estimation will be lower, right? Okay, so I guess starting from team 13, okay, team 18, very unique. Okay, so he added in a comment, how come? So obviously 18, Ying Xuan thought about this. How can this be negative? And when the 2 routers are really, really close, the chance of this appearing then will be higher. So they are probably close enough, very close. And I see that Ethan thought, makes sense, right? And giving something similar. It's negative, so it's probably just not much delay. The delay between the 2 hubs, negligible. Probably. All right, negative delay. Howway, let's see. Howway, you're missing your team number. Okay, guys, please kindly add your team number. Oh, interesting. Howway come up with something different. Okay, so you probably meant -1 here then, because the solution is very straightforward, right? Take the average and then subtract the 2. Yeah, I guess you guys all come up with the same thing. All right. So if any of you have more to add, for example, I ask, how would then one be able to estimate the delay between hub 8 and 9 reliably? What would you do? All right. So that will be the bonus points, okay, for your team. All right, good. I think this is good enough exercise about delay. With the queuing delay, with unparalleled paths going one way, come back might not be the same set of routers. And also there will be sometimes ISPs kind of balance loads among the routers. The delay measurements can vary a lot. Okay, that's the major point here quiz 6 is trying to deliver. Good. Now we go on to talk about the other 2 metrics. First is loss. Okay, essentially what we do is to find out, right, among all these packets we send, how many of them are lost. So loss rate. It's very straightforward. And we heard about why there's packet loss many times. So this video is going to be short, just 1 minute. All right. Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case a packet arrives when the queue there in the router is already full, So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we will not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system is doing the retransmission. All right, so after knowing that there are packet losses, there are different ways of trying to recover from the loss. And sometimes one probably doesn't, specific application probably doesn't want to recover, or there's no need to recover. Good. Now, the third metric is called throughput. The unit of measurement is bits per second. It's the same as the unit we estimate the link capacity. Okay, but link capacity is to estimate how many bits you can push through a link, but throughput is to estimate how many bits you can put through a whole path from the source to destination. Okay. Now this one is a little bit long, almost five, I think slightly more than 5 minutes. Okay. Throughput is the third metric, and it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end, and the speed of data is going through the entire channel, entire pipeline. Now, there are two ways of quantifying throughput. One is called the instantaneous throughput, the other average throughput. Now, the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discussed throughout the rest of the slides will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of F bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network. And the link capacity for the link directly adjacent to the server is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider, okay, such a data pipeline as a fluid pipeline, water pipeline. Then you see I'm drawing, okay, the pipelines with the diameter based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? Okay, a water tank, dumping waters, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS? Well, it's probably not that hard, isn't it? Because the intuition tells you that, hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Okay, even though RC is bigger, yeah, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, yeah, there could be a lot more water coming in, okay, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, okay, RC is going to be the throughput. And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. Okay, so throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, okay? Deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, okay? Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end to end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. Okay, RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming the 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this, minimum of RCRS and R over 10. In practice, however, okay, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an end system, this is an end system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays, there are a lot more connections sharing the big R. Okay? Most of the time, RC, RS are the bottlenecks. But occasionally, you might also see when network is really congested, R is not quite enough to allow all the connections demanding services. All right, now we move on to chapter 1.5. So this chapter is a little bit strange. It's actually, there's nothing technical, okay? So I've prepared a 1-minute opening. Let's just go on to the first video. 1 minute. 1.5, protocol layers and service models. Well, this is a very special section. There's not much really technical here, and the purpose is essentially to explain more. You'll see later in chapter 2, 3, 4, 5. The chapter's title is called something layer, something layer, something layer. Okay, we kind of talk about all these internet protocols or internet mechanisms by grouping them into layers. So chapter 2, we talk about protocols running in a particular layer. Chapter 3, another set of protocols running in yet another layer, and so on and so forth. So 1.5 here is to give you an idea why we kind of classify protocols into layers and what does each layer do in terms of functionality, making sure that the internet operates seamlessly. Okay, so we call that the service model, the internet's service model, or the architecture of how we organize softwares running on the internet. All right, so there are actually 2 major reasons to explain why the network engineers always say that, hey, the protocols this protocol is application layer protocol, that protocol is network layer protocol. Why we always use this layering thing to refer to the protocols. Okay, so the first reason is to enable communication, to establish some common language. Okay, and this next video is to explain that. So Polly is using the experience over the past 3 weeks, okay, how we communicate, to show you that having some structure when we're talking will be helpful. 1.5, protocol layers and service model. Sorry, misclick on the stream deck. Oh, let's recall all the terms we've referred to since the beginning. Right, we've seen hosts and systems. They're essentially the machines composing the edge of the internet. And then the core of the internet, right, the other one at the center of the internet being a mesh of interconnected routers. And then connecting the edge and the core, we do have these access networks or access links. that operates on different kinds of physical media running different kinds of modulation mechanisms. Yeah, access network. So these nuts and bolts compose and form the physical infrastructure of the internet. So this is more the hardware side of the internet. But we also talk about that, hey, hardware is not the only thing that makes the internet work magic today. A lot of times we rely on these applications in order to what? To see a page that we are looking information from. Okay, so applications such as World Wide Web email, and these applications a lot of times, right, it's implemented in a way that there's some part of the application running on one physical entity and then another part running on another physical entity. So if you recall, for World Wide Web, there's the client side on the client machine, and then there's the server, the web server running on the web server machine. Okay, and these are client and server side will need to communicate based on a specific rule. Okay, and so those rule forms a protocol. So there's also a protocol for the World Wide Web. Okay, so this is one example of the software on the internet, and there are a lot of these softwares. Okay, an application is just one kind of software, right? So in terms of software, okay, there are a lot more to talk about, a lot more pieces. In fact, the hardware part, and this is a very simplified view, okay, there are also a lot of other hardware pieces as well. In fact, to talk about a complex system like this, we do have a major question to begin with. Okay, is there a way, a hope to organize these pieces so that it's a little bit easier to teach or a little bit easier to discuss? Okay, not just between the senior network engineers, but also for the incoming network engineers, and how the senior ones teach the junior ones. Okay. Yeah. So doing some classification sometimes speed things up. Speed the rest of the process up. Okay, so we do classifications all the time. We discriminate things all the time. It's just that when it comes to people, we don't want to classify people all that much. Right? Now, there's another reason, and a very, very good reason. So once again, Polly is going to use an analogy. That's air travel. Okay, so internet is a network to communicate data, messages. And air travel is a network as well to what? To transport people. Okay, so it's going to take a while. So this video is 6 minutes. You will see that to transport people over the air, it's a complex system as well. Okay, now in order to manage such a complex system, there's also a layered structure. It's just that it's not that explicit for us. We are the stuff that system is trying to transport. So 6 minutes, air travel. Let me try to use an analogy, air travel here, to show you that it's kind of important to have some sort of organization, some sort of architecture, okay, to make sure a complex system will work seamlessly. And you will see also air travel and internet. Okay. Air travel to communicate people, internet to communicate data. They're somewhat similar, and therefore the architecture used by air travel is similar to the architecture used by the internet. Yeah, by architecture here I meant the service model, the way the service operates. Good. Now, recall your experience traveling through air. First thing you do, purchase the ticket that guarantees you a seat. At the day of travel, you walk up to the counter, you present your passport and the ticket number. They will allow you to check in your bag and give you the boarding pass. With that, you go to the gate and they let you into the plane. And then the pilot will be negotiating with the traffic control of the departure airport and decide which runway and at what time the plane can take off. And then for a long time, you're just sitting in the cabin and try to get some sleep. But the pilot is busy doing this, okay, routing the airplane. Okay, so as the plane crossing border of some air control, communications will go on again and making sure that the planes traveling the air, the space, will not collide to each other. And hopefully everything is fine at the arriving airport. Again, pilot talks to the traffic control and find out the runway and the time to land. When the gate is connected and open, we may now leave the plane. Most of us go to the baggage claim to pick up our bag and exit the airport. So it looks like it's a series of steps. Very simple. But if you think about it a little bit more, right? Purchasing the ticket is important so that it guarantees you a ticket. So that when you go to the counter, when you're trying to check in your bag, they recognize you, right? And the base of the recognition is on the ticket number, okay? Acquired here and checked here. And in return, you get a bag number, which is used again here. You get also what? A C number, which is used again here. So there are still some communication that needs to be done, for example, between the steps, in between these two steps. Okay? So this component here, more closely related to this component. This component here is also more closely related to this component. And this component also connected and related to this component, even though this is at the departure airport, and this is at the arrival airport. Okay. So you see that there are components that are related, and there are some base in order to communicate between the staff members here and the staff members here. Okay, the mechanism here and the mechanism here. But you see also, for example, baggage check here. Well, it has less to do with the pilot communicating with the central control. Okay, you see also a little bit, right? This is a little bit more like the internet core. The functionality is quite different, but these are a little bit more like the edge of the internet, where you're trying to track data. Here we're trying to track passengers and the belonging of the passengers. Okay, and so that it's probably not that hard to see. There's a architecture there, okay, and it's kind of laid out in layers like this, right? This is communication to traffic control, but at the end, communication to air travel on the other end. Communication of air travel, but from region to region to region to another region's traffic control office. Okay, so to regional office, it's just to make sure that the height and the orientation of the travel is correct. Now these involves also runway. So you see there's slight differences between these two layers. Now these three, okay, are more handling the passengers and baggages, not handling the plane per se. Okay, so which gate we get in and which gate we're coming out. So your families and members will know where to go to pick you up, for example, to welcome you back, for example. And baggage here, the number is important. At the destination, you also want to know which station is for the baggage claim. There are usually multiple of them, right? So it's also based on the plane number, the flight number. Similarly, ticketing. Sometimes you need to delay travel, right? So you need to call the ticket office again to try to change the date or change the class, okay? And the reference is always, for example, the ticket number, okay? So for communication, you need certain important IDs, important information there, okay? To communicate within a layer, okay? The claim ticket there for the bag is so that you can pick things up on the other end. But there are also certain numbers. For example, ticket number connects to a bag number. Ticket number also connect to a C number here. Okay, so certain pieces of information might be added there, either to allow communication within the same layer from local side to remote side, or information to allow components across layers on one side to try to relate to each other. Okay, so you see, air travel, okay, is a complex system. If any step goes wrong, it could end up being a disaster. Okay, needs to be well structured to make sure also that it's efficient. So there are layers. Okay, each layer implements a particular function. Okay, a particular subservice. Okay, and so there will be some internal actions, but they will also depend on services or functions provided by the neighboring layers. Okay, from the layers below. Okay, or they might also need to provide supports to layers above. All right, so you see from that analogy, a complex system, a structure is required so that the communications across different functions can be kept minimum. All right, so next video is to say more formally. Now you get a sense what the benefits are. Now next is to give you more formally the two major benefits. Hopefully with the air travel example, you see in large complex systems where we have lots of these pieces, it's really good to have some explicit structure so that it's a little bit easier to identify in case there's a bug, which piece the bug is, and to find out what are the related pieces might be partly to blame as well. So having explicit structure, really good. And you see in the air travel example, we have this layered architecture, layered service model. That's exactly what we're using, okay, to manage, to organize internet's operation. And we call that layered service model also the reference model, because we are referring to these pieces on the internet in layers as well. Okay, so it's our reference model for discussion among the network engineers, okay, which you are becoming one as well. All right. So this way of trying to break a large complex systems into pieces, okay, and to define, okay, the functionality of each piece is also called the modularization. All right. So after defining the functionality of each pieces, after finding out the relationship between the pieces, okay, we implement the individual modules functionality. We also implement the interfaces to communicate from module to module. Okay, so that is called modularization. Okay, this is really common. We see in large software systems, okay, because it's a lot easier to maintain. It's a lot easier to debug problems, and it's also a lot easier to improve the system, to move a complex system forward. Okay, because you see, the important functionalities are well modularized. So if we need to change the way we implement the functionality, we can just change it. Okay, and that change does not need to propagate through the entire system across the different modules. Okay, so a change, okay, in a layers service, a change within a piece, a change within a module, okay, can be transparent to the other modules. Okay, because the APIs are already well defined. There's minimum communications required. All right, so it's just like this. Here's an example. If we change the gating procedure and we decided that we let the first class passengers to go last, hey, it's not going to change how the pilots communicate with the traffic control, right, in order to find out which runway to take off. So each module more or less independent, and the communication across modules, across layers, are minimal. Modularization, or layered reference model, layered service model. Sounds nice. Can you think of anything that suggests such a layering is not exactly good? Okay, so if you can come up with something that says that such a layering is not good, all right? And now we move on to the next topic, the internet protocol stack. So finally, you will see that stack. Okay, we see the stack for the air travel. Now you'll see the stack for internet protocols. So there are several layers, and in each layer, Polly will give you a few examples of example protocols. Okay. Here's the internet protocol stack, and you see here what I'm illustrating. It's in the layered architecture. The layer at the top is the application layer. So these protocols at the application layers are, okay, literally to support the applications. For example, HTTP is supporting the web application. So you do have application processes sitting on the web browser side and another application layer process at the web server side. Okay, and there's a protocol there. For example, a message go out is necessary from the client to request for a web page, right? And that web page will be another message coming back the other way. Well, that's pretty much what HTTP defines, right? So these messages to control when to start sending and which web pages to send. Transport layer, that's one layer down. Okay, the functionality is essentially to allow these application layer protocols to specify, okay, whether these data that I'll be sending through, these data packets I'll be sending through the internet is going to be reliably transferred or best effort transferred. Okay, so this is to administer data transfer from client to server process or vice versa. Network layer protocols, on the other hand, very special. Yeah, all these packets, oh, by the way, packets, when it arrive at the network layer, it's called another name, datagram. So these packets coming from the source, right? It needs to find a way to the destination. You see, at the core of the internet, we do have a mesh of interconnected routers, don't we? A router could have multiple connections to other routers. So each router will need to know, okay, which is the right router to forward next so that the packet will arrive at the destination with the shortest distance possible, right? Because you do want the packets to arrive at the destination as soon as possible. So a good routing protocol is to ensure something like this. So network layer, the protocols there are essentially to handle packets being forwarded and the directions of how these packets being forwarded in the core. Link layer protocol. Okay, so these are very special. They work a little bit like, honestly speaking, the transport layer protocols. Okay, transport layer is to handle data transfer from one process to another. Link layer protocol here also handle data transfer, but it's between one network element to another one network element, one network hardware to another network hardware, or a network entity to another. For example, between two routers directly adjacent to each other, there's just one link. Okay, so this might across several hops at the transport layer, but link layer protocol only handles data transfer in one hop. Okay, so it deals with the data transfer very locally within a link. For example, Ethernet is a link layer technology, a link layer protocol. All right, so that's the internet protocol layers. You know what? This is a perfect time to take a break. So we'll take 10 minutes break and resume the lecture 11:21. Go. All right. Okay. Oh, we're not quite yet 11/21st, but it's okay. Let's go ahead and start because this is the very last video of chapter 1, and it's actually an animation of showing you how the packet travel through the software pieces and the hardware pieces together in one video. With the layered architecture explained, what I'm showing here is the software side of the internet side by side with the hardware of the internet. So where are the hardware in this example? Look, here, and here, and here. So these are end systems, okay? This one is the source, and this one is the destination. You see that at the end systems, the entire internet protocol stack is implemented and running. Similarly for the other end system. But in the core of the internet, you see the router over here. And this is a very special entity, hardware entity. It's called switch. But to be precise, this is the link layer switch. Its functionality is limited. Okay? Unlike router, this is a network layer device that implements the protocol stack from the lowest up to the network layer. The link layer switch is a more limited device. It implements only from the physical to the link layer. Well, then you see how it gets the name. It's a link layer switch. And if you want to be precise, you can also call these routers the network layer routers. Or sometimes we actually call these routers network layer switches. Okay, so both of these entities are doing switching, but doing the switching at a slightly different level. All right, now walk with me and let's see how the data gets passed down the protocol stack, out of a physical entity, and through the network, reaching the destination. The first step is this. One particular user typing things up. So at the application layer, this component generates a message. A packet at the application layer is referred to as a message. The application layer component will pass the message down. As the message arrives at the transport layer, a header is being appended in front of the message. Okay, because it's appending, therefore these additional pieces of information is referred to as the header. H stands for header. And this is a header appended by the transport layer, therefore HT. The whole thing together, this packet, is referred to as the segment. So a packet at the transport layer is called a segment. And you see that this header here is very important. This is to allow the transport layer component at the source side to communicate with the transport layer component at the destination side. Okay, so this is a little bit like at the airport. When we're checking our bag, the counter is going to give us back what? The passport, the e-ticket, and what? The baggage claim ticket. Okay, so that baggage claim ticket, that additional information, okay, in order for you to find your bag, is a little bit like the headers. And now the segment is going to be passed further down to the network layer. And guess what? The network layer component is going to append some more information to it. And that is in the header as well. But this is the header for the network layer, HN. And the whole thing now, the packet here at the network layer is called a datagram. And the whole datagram is going to be passed down further to the link layer. And guess what? The link layer header is going to be appended, and we call a packet at the link layer a frame. So this frame here, now arriving at the physical layer, what physical layer is doing is simply modulating the 0 and 1 bits, okay, onto the physical media. So it's going to go out shortly through the network interface and arriving at the router here. Now I'm skipping the switch here because it's a link layer device. We'll not be able to cover the link layer chapter. So this message is going to arrive here at the router, receive at this physical layer, and the signals gets converted to the digital form. So we restore the original frame back, and that's passed up into the link layer. The link layer at the router is going to examine this header and see if there's any additional function that it needs to perform. When everything is done, guess what? Okay, this header is going to be removed. So only the message with the transport layer header and the network layer header will be passed up to the network layer. You see here, the message is being passed upwards, okay? Because the network layer component of the router still needs to check this, okay, and see if there's something that the network component needs to do at the router. So this is going to be examined, okay, and functionality is performed. Now this part, hey, as this is a router, there's no other layers above. So this is going to be copied over, okay, and stand by there at the outgoing interface. Now before that message go down to the lower layer, yeah, the new network layer header is appended. And this one is a datagram. It gets passed down to the link layer header appended. And this is a frame. It goes to the physical layer, bits modulated, traveling the link and reaching the destination. Similarly, the physical layer is going to recover the 0 and bits and give this up to the link layer. This checked by the link layer and the remaining gets passed up to the network layer. And you see this removed, this part gets passed up to the transport layer. This removed, and this part here gets passed up to the application layer. And here, the destinations processed there at the application layer, finally you see the message coming from the source originally. So this is how a message travels through the protocol stack and the physical infrastructure, and more protocol stack up and down until all the way up to the application layer and the destination. All right, so that you see the life of a packet traveling from the source to the destination. And there's a pop-up quiz. Polly asks, how do we call a packet at the network layer? Okay, I see. Okay, good. Many of you are following the lectures. All right. Okay. And you know what? We are finally done with chapter 1. That is to give you a very high-level view of the internet. Lots of terms. Okay. We'll finally start talking about specific protocols, and particularly next is the application layer. Okay. To start this chapter, what I would do is to actually talk about these applications we see very often on the internet. These are all network applications. To make sure that we're in sync, let's inventory some of the popular network applications here. Email, web, nothing more need to be said. They are obviously email and web. Text messaging, Line, WhatsApp, what else? A Google Messenger. And if you guys are watching this from a YouTube live stream, that chat room is a text messaging app. Remote logging. If you downloaded a client to remote log into the PA server, then you're using a remote logging application or remote logging service. P2P file sharing, the most well-known one, BitTorrent. Okay. Multi-user network games. Okay, so this is a more formal way of calling online games. Okay, so some of these online games are running on desktops, going to the game server somewhere provided by the game company. The client can be nowadays running on smartphones. In fact, probably more games people are playing are mobile games. Okay, so the client is on the mobile platform. And then the multimedia applications. Here we have the streaming stored video, and we have the real-time voice. So this is also called the voice over IP. And we have the real-time video. Okay, well, real-time video conferencing, of course, also comes with audio. Okay, so essentially these three are multimedia applications. The difference between this and these other two is that the video is actually a playback video. So the video is already stored in one of the video content server, and when you request it, it is just playing back the video. But for these are the live video being generated as you guys are having conversation, as we are having conversations. So the delay requirement for live audio video is a little bit higher, more stringent. So what do we have as real-time video conferencing apps? Yeah, Google Meet, the one we have standing by here, allowing you guys to call in, is a real-time video conferencing app. So there are other real-time video conferencing apps such as Zoom, Microsoft Teams. What else? Well, Skype. Although transfer audio, it also transfer video. So Skype is also a real-time video conferencing app. So there are many options here. Social networking. Hey, Facebook, IG. One can probably come up with others such as Snapchat. Yeah, so there are just increasingly more of these social networking apps. search, Google search or Bing. Yeah, each of these is also an application or a network service. Cloud computing, yeah, Amazon AWS, for example, is a cloud service. And you know what, guys? That takes us to quiz 7. Okay, so this one should be relatively easy for you. It's actually serving Polly's purpose more. So quiz 7. So what Polly does is to survey what the younger generations do over the internet. Okay, so that I'm not completely out of the sync because I use analogies a lot, and I need to make sure that you guys can relate with the analogies I give. What's nice about teaching in college is that I have you guys. So here, for quiz 7, I need you to tell me in Q1, the top 2 network applications you use on a PC or laptop. All right, so non-mobile essentially. Q2, the 2 frequently used apps mobile on your smartphone. And Q3, the top 2 games you play on any of the platforms, the games that you spend the most time on. Okay, and that is quiz number 7. Okay, yeah, I forgot to go to the whiteboard mode, but hey, this is what you're asked for. So guys, this one should be straightforward. So you guys have only 2 minutes, all right? Okay, I see students are typing up already. Typing the answers up already. Okay. Andrew, you are the first, but you're missing the team number and the answer to Q3. Okay. So Kaylin, wow. Following the lectures very closely. Good for you. Okay, so Q1, I'll look in Google, so reading emails and looking things up, I guess. Q2, oh wow, TikTok. And exactly, Snapchat, right? One of the social nets I mentioned. And I'm not sure if TikTok or YouTube are video apps. They are probably video social network apps, right? So it's a kind of app that actually serve 2 purposes these days. I don't really have any games. Oh, I think that's a good thing. But on the other end, I guess your parents will also become concerned as well, right? So I guess you have other ways of decompressing. So that's okay. That's okay. Jordan here says Slack. Okay, interesting. Anti-gravity. What is this? Okay, hey Jordan, if you don't mind, can you elaborate what anti-gravity does? Well, of course, Polly will look it up after the lecture, but interesting. See, I need to, ask this question every year because every year I see something new. All right, so on the mobile, you do Line and Messenger. Okay, yeah, it makes sense, right? On the mobile phone, a lot of time you try to that's how you connect, send messages to each other. Pikmin. Duolingo? Is that a game? Okay. Yeah, sure, why not? And 一心 Facebook and Discord, IG and Messenger. Yeah, so social stuff on the mobile phones. Minecraft, okay, that's a very popular game. Pokemon Go, okay. I used to play this for research purpose, but yeah. It never ends. Okay. So I like round-based games. So you have like a closure. But there can be games out there that never ends. Ooh, wow. Sometimes that actually adds stress. Gemini. Oh, cool. 应轩. Yeah, I do find that I use these AI apps more and more. I guess many of you probably do. Just you didn't think of Gemini being a network applications. Yeah, these AI apps, okay, which is not included in the opening video, are also network apps. GeoGuessr. Oh wow, this is hot recently. Thanks to Google. Yeah. This is so cool. Okay, Google and YouTube. Classic, right? Classic Google and YouTube. Yeah, Line, Messenger, Insta, also very common on the mobiles. Pokemon and chess. Okay, chess can sometimes be time consuming. I forget about time playing chess. So I kind of refrain myself from playing more. Okay. Maybe during the winter or summer breaks, but not during the semester. Google and Gmail, again, classic. Messenger and Line. Arknights and GeoGuessr. Okay, so this is the second time it showed. This game shows. Arknights. This is certainly a new game for me, but it might not really be a new game in the market. Let's see. YouTube, Gmail. Line and YouTube. Okay, YouTube. Oh, I'm seeing YouTube more. TikTok, YouTube. Video-oriented social net. Battle Cats. Wow. Look at all these different new games. Telegram. Okay, Sherwin. Okay, you use also WhatsApp. I thought that WhatsApp is going out of fashion, but I guess not quite true. Depending on which region in the world, I guess. Pokemon Go only. Oh, a hardcore player there. I used to have trouble finding students to do game research because many of my students don't play games. Arc line. Okay, interesting. Very interesting. You don't play games. 1010. Oh, okay. So 10-3. I don't know about these games. All right, very good. VS Code. Okay, Yuzheng, you do a lot of coding, I guess. Yeah, I guess we are kind of converging to something. On the desktop, on the mobile, many of these are social and messaging apps. And video apps, definitely more. Don't play games, yeah. So these look like they are mobile games, right? Okay, Ray gave up. I just keep changing. Sure. And Howie, let's see. ChatGPT. Interesting, Spotify. Yeah. I can live without music. Definitely. Spotify. Call of Duty. Okay, these seem also mobile games. Chess, Arena of Valor. Okay, Netflix. Another video app. Oh, okay, so on the desktop, you typically watch videos, I guess. And on the mobiles, you communicate. Very good. TikTok, Spotify. Very American. Or, well, actually, for many regions of the world, this is very typical apps for entertainment, right? On a mobile phone. I don't play a game with an LOL at the end. I don't know if this is expression or the game that you play more often. Arc Knights, the second time I see this. Okay, I'll check this out. So I wonder, right? Gemini, ChatGPT, which one you guys use more often? Also, what? Interesting. I'll definitely try these games, you guys. Okay, Animal Crossing, of course. And hey, this is actually related to quiz number A. Han-en. Okay. Exilium. Sounds funny. All right. Click to see attachment. Okay. Firefox, YouTube, Gemini. Oh, okay. The reason that you use Gemini is because you get a student account. Interesting. So which one is cheaper? ChatGPT versus Gemini? There's probably no student discount for ChatGPT. MBA. So maybe I should rephrase the Q3. I did not mention like game consoles. If I mention game consoles, then there could be other games popping up. God damn. mahjong. You accidentally press answer. Okay. It's okay. No problem. Yeah, you just edit the post. NTU, cool. Wow. Okay. Vincent, very good student there. Okay, that behavior is highly encouraged. You play only this. Okay, Tower of Saviors. ChatGPT and Gemini. Oh, Youcheng, you use both of them. So I guess you ask the same question here and there and try to make sure that you get sensible solutions. Interesting. I don't know. How often you do this? Guys, if you do this as well, just say it in the chat room. Say in the chat. Do you use multiple AI tools and see if you can take the best of the two? Or confirm the answer from one tool from another. Insta and Facebook. Clash Royale. I don't play game. Oh, poor you. Lead code. Okay. Oh, so you are a coder too. And NTU, cool. All right, maps. Hey, you know what, Yasin? On the mobile, Maps is another apps that we use very often, indeed. Good, very good to cross-check what you guys do. okay, these days. Back to applications. Now, let's be more serious. We're going to talk about applications, network applications in particular, because the network applications versus the non-network applications are quite unique. Okay, you will see as a network application designer, what we do in the end is to implement these applications. Okay, and they will turn into processes. And what's different is that very often for a network application, we write multiple programs, and therefore there'll be a process running here, and there's another one running here. So the two ends can communicate, send messages, and we get to know each other on the internet. Okay, so that's the main difference. We have this communication part, and therefore we write multiple programs and we run multiple processes. Okay, and these application layer programs will only run on the end systems, because these end systems are where the users users have access to. So these applications do not run in the core of the internet at all. Okay, so the principle of network applications, that is what the next video is about, and it's brief, 2.5 minutes. Now, to support all these applications, the principle is quite straightforward. Essentially, we write programs. There involves at least two parties. One program sits on one of the parties. Particularly, each of the programs sits on each of the end systems involving the communication. Okay, so they will be communicating, sending messages over the internet. So for example, web server program sits on the web server machine. Browser sits on the client machine. And these two programs send messages to each other. Much like this. So we might have a web client here. We might have another web client here, and the web server is down here. And we establish connections like this. So this client's program interact with the server's server program. This client's program interact with the program running on the server as well. Okay, so you see that the server program here needs to be a little bit more powerful, allowing requests from these clients, okay, frequently and potentially simultaneously. So essentially, in order to create these network applications, we design how the messages are exchanged, meaning designing an application layer protocol. Afterwards, we program the softwares. There'll be one part running on one end, the other part running on the other end. So this example here is a client-server application. For P2P, one runs on peer, the other runs on another peer. But in P2P, these two programs usually are identical because they are both peers. Now, what's unique here is this. Applications run only on the end systems. In the network core, the routers do not run anything particular for a particular application. Okay, so the core devices do not run applications. They do not run specific functions to support individual application. Okay, so applications are strictly on the end systems. So clients, limited devices such as a smartphone, such as a laptop or desktop, are on the edge of the internet. But you see here, servers, more powerful machines, they can be quite expensive. Some of them can be just as expensive as the routers, but these servers are also at the edge of the internet. They are also end systems. Just don't be confused. Okay, so these end systems, there are programs running and exchanging data such that we can perform a specific application or specific service. All right. Now, as a network application designer, there are very often some design considerations, okay? And once you finish considering all these aspects, then you start programming, okay? So the first design consideration is to determine the architecture of your app, the communication model. As I mentioned, that there are often multiple programs you need to implement and how they communicate with each other, the communication model, all right? So in this video, you will see that there are two major flavors, and then the third flavor is kind of mixing the first two. Okay. Sorry. First thing we do designing a network application is to decide its structure. There are three general models, and we'll go through them one by one. First is the client-server model. In such a model, we have powerful machines we call servers that are always on and running on permanent IP address, therefore always reachable, and sitting in one of these data centers allowing access from users worldwide. Now, on the other hand, we have the clients. These are the devices operated by the end users, such as us. So these are the devices initiating communications to the servers. And they are intermittently connected to the internet as we operating these clients are moving around. And so from one location to another location, we'll be using different IP addresses. That is why the clients do not communicate directly to each other, because the IP addresses that each of these clients is using the next moment can be different. So two examples on the left are first, a driver in a car looking up a route to a particular destination, and she could be accessing the Google Maps server. And this can be a student looking up the PA assignment, then this will be the web server of the course webpage. Second is the P2P model. In such a model, there are no longer always on servers. All we have are just a bunch of these intermittently connected end systems. These end systems will be communicating directly to each other. And we call these end systems peers because they will be requesting services from other peers. They might also provide services to other peers. That is saying that these peers, these end systems, are not strictly client or strictly server, and each of them play equal parts. So peers are a better way to characterize these end systems. This is what's nice about the P2P model, self-scalability. When a new peer joins the network, as they request for services, you will see that the demands go higher. But they bring also computation or storage capacity, right? So we get more resources as well. This is opposed to the client-server model, where there are more clients joining. The service demands will rise, but the capacity doesn't. Now, on the downside, the peers are all intermittently connected. That means the IP addresses are changing all the time. So you can imagine that it can be a little bit challenging maintaining a continuous connection. Third is the hybrid of the first two models, and this is used by Skype, a voice over IP service that used to be popular. And in Skype, the call in between two users, that is done by a direct connection between the two users and systems. So you can see that it's P2P. But to establish the call, you need to find the address of the user you want to call to. And that is done by querying a centralized server. So you see this part of Skype is client and server. And so Skype is under such a hybrid architecture. All right, so architecture, kind of straightforward. Next is socket, okay? You see that already that we have multiple processes running on one machine versus another to enable communications across these processes over different machines. We use this thing called socket. In this video, you will see that you will see first where socket is, okay, sitting in the operating system stack. You will also see that when you create a socket, okay, it's straightforward. You just call a function and then you create a socket. What's a little bit more complex you need to consider is what kind of socket you create. And once you decide, you also need to specify where the socket connects to, the destination address. Okay, so this video is almost 4 minutes long. Okay, socket. Okay, this is the first time you hear about this, so pay a little bit more attention here. In a network application, we'll have program running on the client side, server side, or peer side. Okay, and these programs, as they are running on a host, we call it a process. And so what we want to achieve is for these processes to communicate with each other. Traditionally, to communicate two processes within the same host, all we need to do is just call some of the system calls defined by the operating systems that will allow inter-process communication. But for processes on different hosts to communicate, we'll have to send some messages, and this will be done by a socket that we'll talk about shortly. And so the process on the client side will be called the client process, and it is the process that initiates the communication. The server process on the server side will be the one waiting to be contacted. Now, for a P2P architecture, on each of the hosts, we'll have to run both the client process and the server processes so that they can provide services to each other and request services from each other. So socket is this thing that allows the processes to send messages to each other. Okay, think of it as a door. Okay, so the sending process will first shove the message out the door. So the sending process here, shove the message out the door, out the socket. And then the transport infrastructure on the other side of the door here, okay, will then deliver the message over the internet to the socket of the receiving process. And after shoving the messages again through the socket, the receiving process gets the message. So from this line and up, this is the application layer. So everything in this space will need to be defined by the developer. That includes the sending process, receiving process functionalities, as well as the sending and receiving sockets functionality. Now, the socket API is the tool allowing the developer to specify the sending receiving sockets. That includes defining the transport layer protocols to use, as well as a number of other important parameters, such as the port number of the receiving process. The most important parameter to set for a socket is the address of the receiving process. Therefore, you can see that for each process running on the internet, we need a unique identifier. Now let's take a step back. We know already for each host, there's a unique identifier called the IP address. So this IP address will be sufficient to identify a host, but would it be sufficient to identify a process? Not really, because nowadays we see very often multiple processes running on a machine. And so we need something else in addition to the IP address, and that something else is called the port number. Together, they uniquely identify a process running on the internet. Now, some of these processes could be well known, for example, a server process for the web, a server process for email. So they could be running on a well-known port number. So web server is very often running on port 80. Mail server is very often running on port 25. In this example, if we send a message to a web server, gaia.cs.umass.edu, that socket will need to be specified with this receiving address. So the IP address of the machine and the port number the server process is running on. All right, so IP address is to decide which machine it is out there on the internet. The port number is to uniquely identify the process, okay? A unique process running out there on one of the machines, all right? Next consideration is message. So you need to design also the messages each of your processes will send to each other. Okay, so there could be type of messages, and these messages need to be understandable to each of the processes. So this video, almost 4 minutes. So messages. Now we have socket created connecting processes. We can begin to send messages. But you see, what we're talking about here is general application design. So an application can be a little bit complicated. The server could be providing multiple services. So how do we know, right, when the server receiving a message, the client is asking for service 1 or service 2 or service K? And vice versa. The server could be sending a message back to the client. And how does the client know what is the intention of the server? The messages being exchanged between these two processes need to be clearly defined. So that includes the type of messages. So one may be sending a message for a certain occasion. So there could be multiple types of messages defined for an application. Now use World Wide Web as an example. The client typically sends web requests, and the server sends web response. And inside the response that contain the web page the client is asking for. Now, continue to use the World Wide Web as example. Inside a web request, there'll be some fields, okay, we define. For example, time of the request, browser of the request, or language preferred by the user sending the request. Okay, so there'll be fields like this with the values that will contain in the web request arriving at the server. Server knowing the syntax, okay, of the request message will understand exactly what's going on the client side, and therefore send the most up-to-date web page in the preferred language, for example. Now, we also define semantics of messages because, again, using World Wide Web as example, The web response a lot of times sends back, for example, status. Okay, so this is the status of the request. Now, if the client is looking for an object that's no longer existing on the server, you see very often a response coming back saying 404. Yeah, what that meant is object not found. The web page is not found. So 404, that status comes with a meaning. Okay, so we define also the semantic of some of these code words. Now, this is really nice to send code words because you use few number of bits instead of sending longer English strings. Okay, so meaning of the information in the fields. Now, of course, right, this is almost like defining a language. Yeah, the rules, the timing we send the message, and when we receive a message, what kind of message we generate next. Okay, so all four together, the types, the syntax, the semantics, and the rules of corresponding back and forth between the processes. That's called the application layer protocol. So each application defines its own application layer protocol, defining the messages it requires and the syntax, semantics, and the rules of exchanging the messages. Now, many of these application layer protocols are open, meaning if you just Google, you identify, for example, the World Wide Web's application layer protocol. That is actually called HTTP, and it's defining one of these RFC documents. So these protocols are open such that if I want to come up with my own browser, because I know, hey, HTTP requests what the format should be like, the syntax, semantics, and rules, then I can write a browser such that it behaves just like the other browsers following the same RFC document. Same for email. Okay, so these open protocols are nice out there because each one of us can develop independently a new web browser, a new email reader, a new web server, a new email server. Now, many of the applications are commercial, owned by companies. So they do have their protocols, but they are not open. So these are the proprietary protocols. For example, Skype, we talked about using the hybrid model to communicate. It's got its own set of messages and syntax and semantics, but they're closed. It's hard to come up with our own client, a Skype client, such that it works with the legit Skype clients. All right, so essentially till this point, right, considering architecture or communication model, considering what kind of socket you want, and considering the messages and design the proper messages so that your process communicate. So these are the basic components. Once you have these, you can go ahead and code. Okay. The next two topics, QoS and transport layer. So these still require consideration because we kind of we went really fast talking about socket, right? One of the things that when you call and create a socket is that you need to specify what kind of socket you want, what transport layer service you want. Okay, and the reason of saying that is because it really depends on the quality of service you wish to provide to users. Okay, QoS, quality of service. So these next two topics are related to configuration of the socket. So QoS, there are actually 4 kinds of QoS, and it really depends on the applications and really depends on how you think satisfying your user is priority or not. Okay, so 4 QoS in general. Now, in order to know what is the right transport layer service for an application, we need to think a little bit more about the application we are designing. What is the nature of the content we're sending, and what the users might be expecting. The first criteria is called the data integrity. This concerns whether the data needs to arrive without any loss. The key word here is that if the apps are about sending text-based content, for example, a file, for example, a web page, for example, a text message, then users are expecting 100% reliability. If we are sending audio video, it's okay to have some loss. Think about speaking a sentence. If we miss a syllabus here or there, the listeners being human beings, we are intelligent. We can still make up the full sentences or make up for what the speakers want to say by looking at the context before and after the sentence. Second criteria, growingly important, timing. This is especially the case for interactive applications. So the keyword here is interactive. Internet calls, live video sessions, or shooting games, interactive games. Users are indeed expecting low delay. Okay, and you guys know. Third is throughput. Okay, this is sometimes referred to as bandwidth requirement. Nowadays, we send multimedia content, audio, video. Text-based content, it does not require too many bits to send them, so it's not an issue. But for video and audio, we do need a substantial amount of bits per second in order to deliver them, so that the bits after recovery, okay, is in good quality. So if you compare video versus audio, the throughput requirement for video is higher and audio lower. Text, much lower. So we need to somehow guarantee a minimum amount of bandwidth in order for these audio-video communication to be effective. Text-based applications are elastic apps because there's no strict bandwidth requirement. The requirement is elastic. Fourth criteria, security. This is probably nowadays the most important criteria. Are the users expecting we are sending data such that we are protecting their privacy? So these four criteria together, we actually give it a special term. They are also called the quality of service. So before we can define what transport layer protocol we use, we need to think through what kind of quality we will be providing the application service. All right. Don't worry. So these will still sound a little bit abstract to you, although that you know kind of each of the QoS, which type of applications will go with which QoS. It's okay. Let's go over some existing examples and how their designers think the QoS are. And this video is 4 minutes. We're going to run over just 1 minute today. Let's go over a few common applications and see if we could sort out their quality of service requirements, or in short, QoS requirements. First application, file transfer. Transferring files are static objects, most of them text-based. Therefore, in terms of data integrity, we demand 100% reliability. File transfers, we do not expect they arrive in a few seconds. Okay, so it's not delay sensitive. As a result, there's no strict bandwidth requirement. Therefore, the throughput part of the QoS, elastic. You can probably imagine email and web objects. These are transferring also files, email files, transferring web pages, okay, web page files. Therefore, the QoS requirements very similar. The second application here is real-time audio video. So, first of all, the nature of content, audio video, different from text. Therefore, keyword, non-text, it can be delay tolerant. Okay. Another is it's real-time. That means it's interactive. That's another keyword, which means we do have delay requirement. And for real-time, that's showing the audio, video that's happening right now. So the delay needs to be less than hundreds of milliseconds. So you feel like it's happening right now. Audio, video, now there's time sensitivity. Therefore, we need to maintain minimum bandwidth. So there's a bandwidth requirement. And the requirement for audio, lower, video, higher. These days, some users might actually expect even higher bandwidth for video. Now, can you think and push a little bit and see if you know the QoS requirement for stored audio, video? Well, first of all, keyword, audio, video, non-text. Therefore, you can probably guess data loss here is loss tolerant. What about the delay requirement for store audio video? It should still be some requirement, but probably not as strict as the real-time audio video. And you're right. Delay can be a little bit longer. But given that there's delay requirement, the throughput is still hard. We still need to make sure that there's a minimum amount of bandwidth available. And audio video, the bandwidth requirements are because of the nature of the content. So it will be the same. Audio, 5 kilobits per second to a megabits per second. Video, 10 kilobits per second to 5 megabits per second. Now, what about this one? Yeah, interactive. The keyword is similar to the real-time nature of this application, isn't it? Except that this is now game data. So you can imagine, delay requirement here, just as strict as real-time audio video. Is it loss tolerant? It's a little bit tricky, isn't it? What about throughput? If there's delay requirement, then there's usually a throughput requirement, but it should not be as high as video or even audio. So here, just a few kilobits per second. Game, this part is debatable. For some games, for example, shooting game, some of the players would argue, I want no packet loss. Okay? But for most of the interactive games, it's okay to have some loss. Okay? And then the users, the players, can try to repeat actions to make it up. What about text messaging? Keyword text, so no loss, obviously. Throughput? Yeah, it depends a little bit on the delay sensitivity, isn't it? And text messaging these days, yeah, it's also debatable whether it's time sensitive. Some would say yes, some would say no. Okay. But you see also that the delay we experience in text messaging, most of them are probably thinking delay, not network delay. All right, now you see why Polly said that which QoS you would like to ensure depends on your audience, depends on your user population. All right, before we go, Katie asked a question. How do you distinguish data integrity and security? That's a very good question. So let me go back to the full QoS. The data integrity we meant there, okay, on the side, is that when there's no malicious party involved in the communication, how do we ensure the data arrive at the destination reliably? Meaning no packet drop, meaning in case it's going over the wireless link, then there's a likelihood of noises around and then causing bits to flip. So in the end, at the destination, you might receive data, but the data is actually false. Okay, so that's the kind of data integrity we were talking about on the side. But I can see that data integrity and security can be related these days, as there are quite a bit of malicious parties on the internet, somewhere in the middle, that's turning the bits, okay? And these can be serious issues, okay? I think some of the scams, okay, are the result of a malicious party there altering the communications between us and important servers such as bank servers. Okay, so security these days, a good part of it is also to ensure data integrity. So the kind of data integrity we talked about on the side is a little bit limited, assuming no malicious party. And you can see also that to ensure data security, data integrity for security, that is a much harder task. Okay, usually involving the use of encryptions, okay, and coding. So Katie, we'll see what people have tried to do designing protocols, okay, in the application layer to help with the transport layer protocols, okay, to ensure real data integrity. Okay, that will be actually next week. All right, Katie, hope I see you, and hopefully you get an answer from there. All right, and that's all the time we have, and this is when I say goodbye. I'll see you next week. Okay, bye. Oh, okay. Interesting. Block blast. Oh, okay. Oh, okay. Okay. All right. So let me go off the stream while I grade.